Welcome back, young physicists. Ever wondered how we turn a boring, non-conducting chunk of silicon into the superstars of electronics? We simply give it a performance boost with a little something called doping. Nope, not the illegal kind. In physics, doping is totally encouraged. So, let's start with the basics. Pure semiconductors like silicon and germanium are called intrinsic. But their conductivity, well, it's like trying to toast bread with a candle. Pretty weak. That's where extrinsic semiconductors come in. We take the pure version and dope it with a pinch of specific impurity atoms, boosting its charge-carrying abilities by a huge margin, sometimes by millions of times. Here's how it works. Depending on what we add, we can introduce either extra electrons, making it an N-type, or extra holes, giving us a P-type. The best part? Even with all this, nature insists on balance. So, charge neutrality is always maintained. That means the number of free electrons always equals the number of positively charged donor ions, and similarly for holes and acceptors. And if you're wondering how this affects the flow of electricity, here's the magic equation. Electrical conductivity, sigma, is equal to N times Q times mu N plus P times Q times mu P. In words, that's conductivity equals number of electrons times the charge of an electron times electron mobility plus number of holes times the same charge times hole mobility. Simple math, electrified. Alright, party time for the electrons. Let's talk about N-type semiconductors, where electrons are the rock stars and holes just tag along. Here's how we make one. Start with silicon or germanium and dope it with a pentavalent atom. That's an atom with 5 valence electrons, like phosphorus or arsenic. Now, these guest atoms bond nicely with 4 neighboring silicon atoms, but wait, one electron is left out without a bonding buddy. Tada! That extra electron is set free to conduct electricity. With so many free electrons roaming around, they become the majority carriers, while holes stay in the background as minor players. That's why this type is called N-type, N for negative charge carriers. Now, something cool happens at the energy level. These donor atoms introduce new energy levels just below the conduction band. And because the energy required to push electrons up to the conduction band is extremely small, around 0.01 electron volts, they jump up easily, especially at room temperature. Picture this, if we draw the energy band diagram, you see a bustling conduction band populated with electrons and donor energy levels packed right underneath, feeding that rush. It's not just physics, it's semiconductor drama. Now it's the hole's turn to shine. Let's dive into the world of p-type semiconductors, where positively charged carriers call the shots. This time, we take silicon and dope it with a trivalent atom, something like boron or aluminum, which has only 3 valence electrons. Aha! One less than needed for complete bonding. So what happens? A neighboring silicon atom donates an electron to fill the gap, and in the process, creates a hole. These holes, the spots where an electron could have been, now act like positive charge carriers. And because there are so many of them, holes become the majority carriers. Electrons are still there, but they're outnumbered and outpowered. Want to know where the action is happening in energy terms? Acceptor atoms introduce an energy level just above the valence band. With a tiny energy gap of about 0.01 electron volts, electrons can easily jump up from the valence band into the acceptor level, leaving behind, you guessed it, holes. In the energy band diagram of a p-type semiconductor, you spot the acceptor levels hovering just above the valence band, and a dramatic rise in hole population within that valence band. It's like a semiconductor soap opera, and the holes are stealing the spotlight. Ever walked into a room and instantly sensed who's in charge? Well, in semiconductor land, majority carriers always dominate, and in N-type, that's electrons, while in P-type, it's holes. Here's what makes extrinsic semiconductors truly special. Their majority carrier concentration is way higher than the minority. Mathematically, for N-type, N is much greater than P. Number of electrons is far bigger than number of holes, and it's the opposite for P-type. But nature plays fair. The system always keeps its charge neutral. The formula that ensures balance is number of free electrons plus number of ionized acceptor atoms equals number of holes plus number of ionized donor atoms. In symbols, that's N plus Na minus equals P plus Nd plus. Now let's talk movement. Electrons are quick and agile. Picture them as caffeinated sprinters, so they generally have higher mobility than holes. Mobility, denoted by mu, equals drift velocity divided by electric field. Because of this higher speed, N-type materials usually conduct electricity better. Putting all of this together, conductivity equals charge Q times open bracket N times mu N plus P times mu P close bracket. And in extrinsic semiconductors, we often ignore the minority carriers in the equation because their impact is so tiny. Okay, let's spy on what's really happening at the microscopic level. It's energy band diagram time. In an N-type semiconductor, donor atoms bring energy levels just below the conduction band. This tiny tweak means electrons don't need much of a push to leap into the conduction band. Result? A bustling cloud of free electrons zipping around, driving current. For p-type semiconductors, acceptor atoms create energy states right above the valence band. That lets electrons easily jump from the valence band into these acceptor levels, leaving behind holes that act as the main current carriers. So, in both types, the energy gap between the impurity level and the nearest band, whether conduction or valence, is super narrow. That's why even at room temperature, a good number of majority carriers are generated effortlessly. Let's flex those mathematical muscles with a quick but classic example. Imagine we've doped silicon with phosphorus, a donor atom, at 1 part per million. That's tiny, like adding a single grain to a ton of rice. Still, in semiconductor physics, even that matters. The question is, what's the majority carrier concentration? We are told the atomic density of silicon is 5 times 10 to the power 28 atoms per cubic meter. We simply multiply this with our doping ratio. That's carrier concentration N equals doping fraction F multiplied by silicon atom density Nc. So, N equals 10 to the power negative 6 times 5 times 10 to the power 28, and that gives us 5 times 10 to the power 22 electrons per cubic meter. Whoa! That's a lot of electrons. We've effectively created a highly conductive material, almost in the range of metals, from a humble semiconductor. Just a pinch of phosphorus, and boom, silicon becomes a current-carrying champ. Let's bring it all together, superhero style. The electrical conductivity of an extrinsic semiconductor is given by Q times open bracket N times mu N plus P times mu P close bracket, where Q is the charge of an electron, N and P are the concentrations of electrons and holes, and mu N and mu P are their mobilities. In N-type semiconductors, electron concentration is much greater than hole concentration. In P-type, it's the reverse, more holes, fewer electrons. Mobility, which is velocity per unit electric field, is usually higher for electrons. That's why N-types often conduct better. And remember, Nature always balances the books. Charge neutrality is given by the equation N plus Na minus equals P plus Nd plus. Here's the big idea. Doping transforms silicon or germanium into powerful conductors by adding electrons or holes. These impurities also introduce new energy levels near the existing bands, a tiny change with a massive effect on behavior. And finally, energy band diagrams show us exactly how this microscopic shift plays out in macroscopic performance. So next time you touch your smartphone screen, remember, it all begins with a few tweaked atoms in a crystal. That's the magic of extrinsic semiconductors. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.